Hi, I'm Izzy Shen, and I'm going to be doing problem number 55. So problem 55 says, a hawk is flying horizontally at 10 meters per second in a straight line, 200 meters above the ground. A mouse it has been carrying struggles free from its talons. The hawk continues on its path at the same speed for 2 seconds before attempting to retrieve its prey. To accomplish the retrieval, it dives in a straight line at a constant speed and recaptures the mouse at 3 meters above the ground. Part A asks, assuming no air resistance acts on the mouse, find the diving speed of the hawk. Part B asks, what angle did the hawk make with the horizontal during the descent? And Part C says, for how long did the mouse enjoy free fall? So, for Part A, I started by finding all the different components of the mouse because the mouse is the part that's in free fall. So if you make a T-chart and you have VI, VF, A, T, and delta X, and you have those moving in the X and the Y direction, you're given that the velocity initial in the X direction is 10 meters per second, and because it's in the X direction, there's no acceleration, so that becomes 0 meters per second squared, and that means VF is 10 meters per second as well. And then you're also given that because there's only horizontal velocity, that the velocity initial in the y direction is 0 meters per second. And then you know the acceleration is 9.8 meters per second squared. And I defined the ground as 0, so everything above the ground is still positive, so your acceleration downwards will be positive. So then I also found that delta x in the y direction is 197 meters because you're told that the hawk is 200 meters above the ground and he catches the mouse 3 meters before he hits the ground. So that means the mouse traveled a total of 197 meters in the y direction. So then I used that information and plugged it into the kinematic delta x equals VIT plus 1/2 AT squared using the y components. And I wanted to do that to solve for t. So I know that VI is 0, so that cancels out. So then I plugged in 197 meters equals 1/2 times 9.8 meters per second squared times t squared, which gave me a time of 6.34 seconds. So then that's the same in the x and the y direction, so I use that on both sides. And then I also want to find the distance the mouse traveled in the x direction because that's going to be used later to find the velocity of the hawk. So I used the same kinematic delta x equals VIT plus 1/2 AT squared. A is 0 in the x direction, so that cancels out to be 0. Delta x is what we're trying to find, so that equals 6.34 seconds times 10 meters per second, giving us a change in x of 63.4 seconds. Or meters, my bad. So then we can take what we learned here and plug it in to find the different parts of the hawk that we wanted. So hawk. So what we're trying to find for the hawk is the velocity initial total. So to find the velocity initial total, you need to find the velocity initial in the x direction and the velocity initial in the y direction. So I set up a similar T-chart to the one I had on the other side for the mouse. So x, y, vi, vf, delta x, a, and t. So the problem says that the hawk starts its descent to catch the mouse 2 seconds after the mouse drops. And because we know that the time was 6.34 seconds that the mouse fell, that means that the hawk started to descend at 4.34 seconds, and that's the same on both sides. We're trying to find VI. We don't know VF. We know the change in the X is 63.4 meters, and we know the change in the Y is 197 meters, which we solved for in the previous part. Acceleration in both parts is 0 because it says it's going at a constant velocity, which means that there's no acceleration. So I took these, plugged them into the same kinematic that we used before. So we have delta x equals VIT plus 1/2 AT squared. And I'm going to solve for the y component first. So I have VI equals 197 meters, and because acceleration is 0, that cancels out, divided by 4.34 seconds. And then that gives us VI equals 45.39 meters per second. So now I'm going to do it in the x direction. So delta x, I'll do this sub y, equals VIT plus 1/2 AT squared. Once again, this cancels out because acceleration is 0. So then we end up with VI equals 63.4 meters divided by 4.34 seconds. And that gives us a VIX of 14.61 meters per second. So here we have the individual components of the velocity in the x and the y direction. So if you were to look at this as a triangle, this is the y and that's the x. So we have this, so this would be 14.61. Oh wait, no, sorry, my bad. This would be 45.39 and this would be 14.61 meters per second. But you're trying to find its average velocity, so it would be this that you want to find, which is the hypotenuse. So I would use the Pythagorean theorem and just do C equals the square root of 14.6 meters per second squared plus 45.39 meters per second squared, and then C equals 46.5 meters per second, which is the velocity of the hawk during its descent, which is the answer to part A. So then part B is asking for the angle that the hawk does its descent at. So the angle, keep in mind that this is the horizontal. So is what we're going to call, we already defined the ground is 0, but this is just another horizontal. So anything below this is going to be considered negative. So this is theta, and then we can use the same measurements from over here that we used. So we do 45.39 and 14.61 meters per second. So then I used cosine theta, and I also used 46.5 meters per second, which we solved for here. Cosine theta equals 45.39 divided by 46.5, both of those meters per second, which gave me an angle of 12.54 degrees. So that's the theta, which is inside the triangle, but what you're trying to find is the outside, because that's the angle that it went from the horizontal. So because we're here, if you looked at this like a unit circle, you're in this quadrant, you're in the fourth quadrant, which means that from here to here is negative 90 degrees. So you do negative 90 degrees plus 12.54, which would give you 77.46 degrees, or negative, sorry. And that's the answer that you want for that. And then part C is just asking for the time that the mouse is falling, which we solved for all the way up here. So the answer for that is 6.34 seconds. So that's problem 55.